So before we begin doing like practice problems about these things, we need to know what a parametric equation is. And honestly, I don't blame you for not knowing because I didn't even know until like 3 days ago. I'm not even kidding, which is kind of embarrassing, but I just know how to do them. I didn't know what it was. So let's say you have some curve like this. Now this obviously isn't a function because a function has to have only one y value for every x value you put in. That's called the vertical line test. And you can see here at like an x value like this. You have this value, this value, this value. That could all be possible answers. So this is not a function. So what people do to get around that is they make it so, let me get rid of this last arrow. Yeah. They make it so these x and y values are given one more variable, which is that movement along the curve. So instead of it just being a curve and then like at some point you have a value, you're moving along this curve. So a lot of the times we denote that, that third variable that they use to make it so you're moving along the curve is called a parameter. So that's why it's called parametric equations, because there's a third parameter that helps us make this into like a function. And a lot of the times we just call that parameter t. Now, that doesn't necessarily mean that t stands for time, but pretty much all of the time that t is going to be doing it's going to be in time. Like, you can make the third parameter whatever you want. This could be like z, this movement part, but most of the time it's just t. So a parametric equation is not going to have points of x and y because we need that third parameter to make this non-function into a function. So the points are going to be x of t, y of t. On College Board, they're going to use t's, okay? So whenever you see a point that looks like this and not like your normal x and y, you know this is parametric equation, okay? So this is how we get around that issue of not having a function when we need a function. So the biggest thing that you need to do with this is, by the way, these things, they act exactly like x and y functions. I mean, they look like x and y functions. Because they are. When you put this parameter on it, it becomes a function. Because now you're moving along here, and it's not like this point is like have all these issues. Anyways, so a lot of the time you're just gonna be asked like, I don't know, to integrate or derivative. What is it? Differentiate or integrate. And all you do is you just integrate each of them separately. So like if they wanted the rate of change, you would just integrate this one. I mean, differentiate this one, and then differentiate this one. Oops. Okay, so you differentiate both of them. They're like a pair. And then the most important thing that you need to remember for parametric is how to find like arc length. So like the distance along a curve. So all you're gonna do, I'm gonna write it like this. Arc length. Okay, this is for parametric, okay? It's gonna be integral from a to b, whatever your interval is, square root, and it's gonna be the derivative of this one and the derivative of that one, so, but squared. So dx dt, and it's dx dt because it's with respect to t, squared, plus dy dt squared. And then you need a dt at the end because it's an integral. So that's how you find arc length. So if we go back up here, there's a parametric equation somewhere. Oh, here. So this question it has to do with parametric. And how do I know? Well, I see this point here. They call the position of the boat x sub t, y sub t, instead of just x, y. So then I'm like, okay, this is about parametric stuff. And they gave us the derivative of both of them. And then what they want us to find is the total distance traveled by the boat. So we don't know what x and y are, but the regular x and y would give us the position. But we do have these x prime and y prime. So what we want to do is we want to integrate both of them to get to x sub t, y sub t, and then that'll give us this point. Okay. But actually, so total distance traveled, this is hinting at arc length, because arc length is a distance. It's the distance. So if this is like, oh, by the way, an arc is just like a segment of a circle. So like from here to here is like an arc because it's arcing. Okay. But anyways, arc length, that's the distance from here to here. So when they say total distance traveled, you should think distance is a length, like a measure of length. So, and this is a parametric question. So I want to use the arc length formula. Okay? I'm going to say that one more time. Distance is a measure of length, and this is parametric. So I want to use the arc length formula. So that's what I did here. From A to B, and you just have the derivative of your x function and the derivative of your y function, both of them squared and added to each other. Oh, and under the square root. And this was a calculator problem, so I put in this into my calculator. Oh, and the distance from 0 to 1, and it tells us that from 0 to 1. So make sure you read the problem, because it'll literally tell you the things that you need to plug in. So I put this into my calculator, squared, plus this squared, and then I square rooted that whole thing. And then it was on the interval from 0 to 1. And that gave me this. So this tells me, and I know the unit is meters because we're talking about a distance, and just distance. It's not like change or like the speed of the boat or like the acceleration of the boat or anything. It's just distance. So it's just meters. There's no per second or per second or whatever. Okay, so that's how I know what the unit is. But also you could think of it like time is measured in hours, and this is the derivative. So this is how fast it's moving. So it's moving at a rate of meters per hour. Yeah, it's moving at a rate of meters per hour. So the stuff in here is in terms of meters per hour. So I'm going to write that like this, actually. And then this dt is in terms of just hours. So, and these are multiplied to each other. Like, yeah. Hour. And I'm going to put it over 1 so you can really see. So these hours like cancel out and you're just left with meters. That's also another way you can find your units. Just take the units of whatever is in the integral and then take the units of what you're like integrating with respect to, multiply them to each other, multiply it out, you'll get this. It's pretty much the same thing with derivatives. When you have like a, let's just use this example again. It's in terms of meters per hour. When you take a derivative, it's like d blank dt, because we're taking with respect to t. So this would be like 1 over like some hours. So when you write the derivative, if we were to take the derivative of this, the units for x double prime would be meters per hour per hour. And it's easier if you just write it per hour per hour. You don't have to do like per hour squared. Anyways, we're getting off topic. Yeah, so parameter, plug in your stuff, get the answer, boom. This was my explanation of the parametric thing. Okay, so that's how I knew this one was about parametric. So you want to remember that arc length formula. Let me see if I have that. Oops, that's not what I wanted to press. Image. No, it's not there. Oh, don't mind my images. Okay. Well, that's literally it for parametric. Let me see if I have another parametric question somewhere here. Maclaurin series. Polar. I'll go over polar in a minute. That's a graphical analysis. This is series. Oh, by the way, I'm pretty sure this is that. I don't know if you remember, but Mr. Palmer was talking about a boiled potato problem that his students have a hard time with a long time ago. So this is from 2017. This is about that boiled potato. I don't know if you remember, but they had a really hard time. So whenever the variables are like confusing you, like there's an h there and there's dht, like just change it back to terms of x and y. So like this could be rewritten like dy dx, and this is negative 1/4 y minus 27. And then, you're just separating the variables, so this would go back there. Well, I'm assuming if I were to like integrate it. And then I would move this back over here, so it would be like negative 4 1 over y minus 27 dy equals dx, Yeah, and then you just put the variables back. So I made the h into a y and then this into an x, so that's like what it actually looks like. But this looks so much more confusing than this, because we're used to this, but we have never used these variables before. So just whenever you get stuck with that, try writing the variables back in x's and y's. Same thing with this. Okay, anyways, parametric. Well, I don't know. So I have like a lot of practice problems here. Okay, well, I can't find any, but okay, I'm gonna make another video about vectors and polar and stuff. This one was pretty short, huh?